Encouraging. Okay, so this last talk of the day, the topic is a rather controversial topic, in the sense that there's a lot of debate of whether we can actually perform quantum computation in the presence of noise, whether the model of noise is really the physical model, etc. And then there's also many mathematical questions about quantum error-corrected codes and what type of codes we can design, so there's a lot of activity in that. When Shor's algorithm came out, basically everybody was very excited, but many people just said quantum mechanics will not allow to run this because this will depend on too accurate evolution of the system, and we know that quantum mechanical systems are very fragile. I'll describe in a moment what I mean by fragile. And maybe this is just theoretical, it's good for ideal quantum computers, but it will never be able to be in reality. Okay, and so, but then came the invention and discoveries of quantum error-correcting codes, which basically showed that from a different point of view, looking at the question from a computer science point of view, allows one to actually correct quantum errors, assuming that the model of errors is really local, and also to perform fault-tolerant quantum computation, which means that if the noise is below some threshold, you can actually perform the computation as if it was in an ideal situation with no errors at all, with an overhead which is moderated. So basically, assume that the error is local, assume that the model that we're working with is correct. Theoretically, the question is resolved, settled. Experimentally, the jury is still out. Okay, so let's start. What's a classical error-correcting code? So we'll first start in the setting in which we want to send information in a noisy channel, but we start with in my lab, say I want to send some a few qubits to Andrea here, and the channel is noisy, but both our labs have quantum computers working amazingly well in both places, okay, with no noise at all. So what do we do? Okay, so first of all, what do we do in the classical world in order to protect the information against the noise in the channel? So what do? The simplest thing that we can do with information. Sorry? Redundancy. The simplest code is just to take 0. Take a blue 0 and just repeat. Say 3 times or many times, and take a 1 and repeat. And then another noisy model in which the probability for each bit to flip is small and is independent. We can assume that the number of errors is small, say that the number of errors here will be only 1, and so only 1 bit will flip. And then what do we do in order, what would Andrea do to decode? Majority. Okay, so say a bit was flipped, 0, 1, 0, then you take majority, or 1, 0, 1, 1, 0, 1, you take majority. In fact, of course, this is a full subject of error-correcting codes, in which you take k bits and you encode them into n bits. And you want the encoding to be such that, so k bits, you have 2 to the k possible messages. and their length is n bits, so they're out of 2 to the n possible strings. But you want these 2 to the k messages to be spread in the space of all 2 to the n strings in such a way that every 2 messages are far in Hamming distance. Let me know if I'm using terminology that is not known for some people. So if 2 strings would be far in Hamming distance d, at least, then if at most d over 2 errors, less than d over 2 errors occurred, I can correct, in theory, information theoretically, by how? Sorry? Yeah, taking the closest code word.
It's not absolute. It's, when you talk about distance, it is not the number of different bits, but the ratio.
I can talk about both.
Yeah, just now, what is d?
Here I meant the number of bits.
Oh.
So if less than d over 2 bit flips occurred, I can just correct to the closest word and I will know. Okay, there's a full theory of linear error correcting codes in which these are linear subspaces, etc. Okay, so so now, what was the worry of people when thinking of trying to mimic the thing to the quantum world? Well, there are several things that worried people. One, well, this repetition code, for example, is impossible right from the start in the quantum world because of the no-cloning theorem, which you had in yesterday's exercise and you're all familiar with, right? Should I repeat it?
Yes.
Yes. Okay, thank you. Cool. So what's the no-cloning theorem? The no-cloning theorem says that if you have a state alpha, you want to copy it several times, alpha to alpha, alpha, alpha. That is not a linear transformation. So alpha 0 to alpha alpha does not exist for all alpha. Meaning there is no unitary that for all alpha does this. Okay? And the reason is simple. Because if there was a unitary like that, it would have taken 0, 0 to 0, 0, and 1, 0 to 1, 1. But then, what would it have done to 0 plus 1, 0? Like to the state plus 0. By linearity, it would have taken it to 0, 0 plus 1, 1, which is not what we want. It's not plus plus. So you can copy in a particular basis, but you can't copy an unknown state. Okay, so that was the first worry. The second worry, which was maybe more, I don't know, another worry, was you cannot, suppose you do something, you manage to encode, but then you want to correct it. How would you correct it? You will start to measure it, but the moment you measure, you collapse the state, you've ruined it. How do you correct without measuring? Okay, so that was another worry. How to correct without collapse of the state. And then another worry was that, well, if we want to encode quantum states, the errors are continuous. They make continuous changes to the state. How could we change? How could we correct for these this infinite number of possibilities? It seems like this would be very hard to do. So I don't know. Let's put it like continuity. Okay, so let's try nevertheless. So our first quantum code will be a 3-qubit code that takes 0. Let's just try to see what happens when we take the repetition code and do it in the quantum world. So 0 will go to 0, 0, 0, and 1 will go to 1, 1, 1. Suppose a bit flip happened. Suppose, what is a bit flip? An x. So suppose a unitary of the form of x happened, say, on the left qubit. So suppose the error was e equals x on 1, and we have x1, 0, 0, 0, which is 1, 0, 0. And the same error on 1, 1, 1 took me to 0, 1, 1. Okay, how would you correct that? You can, right? I mean, it is possible to correct it by just applying another bit flip in the other. Another bit flip will correct it. But in order to know that this bit flip has occurred, you needed to measure the state. Is it problematic to measure the state here? Now, at this point, if I just use 0 or 1, it's not problematic. It is problematic if I encode A0 plus B1 with this code, and so what I get is A0, 0, 0 plus B1, 1, 1. And now if I measure the state after a bit flip occurred, so again, this will be A1, 0, 0 plus B0, 1, 1. If I measure it, I collapse it. Okay, so I think the first key step to understand polymer correction is to understand that, or to recall this notion of projective measurements. Projective measurements. Remember, projective measurements describe a measurement as a collection of subspaces or orthogonal subspaces, a Hermitian matrix whose eigenspaces are orthogonal subspaces, and the projective measurement projects on the orthogonal subspaces, on one of them, and they can be not one-dimensional but more-dimensional. So let's see how we can use this idea for correcting here. So suppose I just want to correct a single x error, but I don't know where it happened. Okay, so this is the scenario. The possible errors are either nothing happened, or x happened on the first qubit, the second qubit, and the third qubit. And I don't know what happened. Okay, so what are the possible states that I have? Either nothing happened, that's this state. I mean, that's the first option. X happened on the left qubit, that's this option. Another option is A0, 1, 0 plus B1, 0, 0. Just testing, okay. And D, A0, 0, 1 plus B, what? 1, 1, 0. Okay, and I'm saying, what I'm saying is that it is possible to distinguish between these four possibilities, regardless of A and B, by some projective measurement, which will not completely collapse the state. Do you see which measurement it would be? To describe the measurement, just describe the eigenspaces. Okay, that would be the first space. So the first space would be the span of 0, 0, 0 and 1, 1, 1. I need 4 spaces in order to know whether this is this state, this, or this. So the idea is, think of a measurement of these 3 qubits, which is defined by the following 4 subspaces. The first subspace is 0, 0, 0, 1, 1, 1, the two-dimensional subspace spanned by these. Another subspace is the two-dimensional subspace spanned by these. 0, 1, 0, 1, 0, 1, and 0, 0, 1, 1, 1, 0. Okay. So suppose I can perform such a measurement, and these are just 3 qubits. Suppose that I'm okay with performing it. Yeah.
So just immediately, the premise here is kind of clear because you typically are going to be doing this with some sort of system of identical particles or something in a real quantum computer, right? So same thing between.
Oh, we're not assuming it's identical particles. Particles are marked. We know where our first qubit is and our second qubit is. Otherwise, we wouldn't have been able to do quantum circuits as well. Like, we need to know where we apply the gates. Okay, so if I perform this measurement with respect to this subspace, this subspace, this subspace, this subspace. So note that these subspaces are orthogonal to each other, right? Yeah? I'm trying, is this a yes? Yes, okay. So if I measure with respect to these subspaces and I start with such a state, what would happen? What would I get? I'll get that the state collapses to this subspace, but nothing happened to it. And the same for this, etc. So this measurement will just tell me which error occurred, but it will not ruin the coherence between the two states in the subspace.
Only if it's correct. If it wasn't correct, it will collapse.
No. Even if it wasn't correct, but only one error occurred, it will not ruin the coherence. Here it was correct, but now one error occurred on the left. So that's, the error was x1 here. The state is this, and it will collapse to S1. And I will know that the qubit that had an X flip was the leftmost qubit, and then I will apply this X and I'm back to my original state.
What's the measurement that you're talking about?
So the measurement is defined by these orthogonal subspaces. So I've defined the projective measurement as an operator here on 3 qubits, it's Hermitian, and it divides the space to a direct sum of orthogonal subspaces, and the measurement projects on one of them. Yeah, remember this projective measurement? You were in the first talk? Okay. So that's how we define a measurement. So let me remind the definition of a measurement. A measurement in general is described by a Hermitian operator. Hermitian operator is something that can be diagonalized, and it has eigenspaces, orthogonal eigenspaces. And the measurement, the process of the measurement is take the state and project it to one of the eigenspaces. The probability to be projected on a specific eigenspace is the norm squared of the projection of the state on that eigenspace. So just in case this might help, I've spoken about this measurement in the first talk. Measurement described by this Hermitian operator that divides the space to two subspaces, one of 2 dimensions and the other of 1. Here, what's the dimension of M as a matrix? 8. It's 8 by 8. Okay. Good. So this solves one of the problems at least. It shows that we can have a quantum error correction process with a partial measurement. We don't completely measure the state so that we know exactly what's the state after the measurement. We get some partial information. We project on some subspace of a larger dimension, and the state within the subspace may be various things. Okay? Okay, yeah.
The other thing is this really the most general setting for an error?
No.
Okay.
Right. Right, so we have not solved, this is not a quantum error correcting code that can correct a single error. It can correct a single error of a type X. Okay, but now let's see, can it correct a single error of type Z? Suppose I now take the state and I apply Z on the second qubit here. What would happen? What would be the resulting state? Z is 1, 0, 0, minus 1. So it takes 1 to minus 1, and it takes 0 to 0. So what would be the resulting state when I take my state and apply Z on this qubit? Minus B. It will get a minus here. Okay? Is this a valid state? It's also in my code because I could have decided to send A0 minus B1. So there's no way I can detect this error. Okay, so I cannot correct the Z error here. Okay, so any suggestions maybe inspired by Thomas' talk about how to correct a Z error? I want to now design a quantum correcting code which only corrects a Z error, not an X error. A single Z error on any qubit. Sorry? Use the X eigenbasis instead of the Z eigenbasis. So now I do exactly the same thing, but instead of zeros and ones, I use pluses and minuses. So I'm encoding 0 to plus, 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 and I'm encoding 1 to minus, minus, minus. And I need to check that a single Z error will also somehow define orthogonal subspaces that I will be able to detect. So what does a single Z error does to a plus? Makes it a minus. So everything here is exactly the same, except zeros are replaced by plus and ones are replaced by minus. So a single Z error, if no error occurred, we will have here plus, 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 and minus, minus, minus. Okay, maybe I'll do it. So if no error occurred, I have A0, A plus, 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 plus B minus, minus, minus. If a Z error occurred in the first coordinate, then this will be flipped to minus and this will be flipped to plus. So I have minus, plus, 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 minus, minus, and everything else is the same. And the last one is plus, plus, minus, plus B, plus A, minus, minus, minus. Okay. A plus, thanks. That was, I wasn't checking. Okay, so these are the states after the mistake, single mistake. And again, I can define exactly the same subspaces, two-dimensional subspaces, but in a rotated basis. Exactly the same. The first space will be spanned by these two states, the second space will be spanned by these two states, and all these states are orthogonal. Why are they orthogonal? Because the inner product between this state and this state is the inner product between these two, which is 0, times this 2 times these 2, right? So they're all orthogonal. It's enough that they're orthogonal in one qubit for them to be orthogonal. So we have 4 subspaces, which again, if we measure on one of them, we know what's the error we can correct. Great, so we can correct the Z error. What happens with an X error now? Now suppose an X error occurred here. What does it do to this thing? What does X do to plus? Nothing. What does X do to minus?
against it.
adds a minus sign in front of it. So I'm getting the same problem exactly, except on a different basis. So I've managed to correct z, but now I can't correct x.
You could do the tensor, right? Just make it longer.
Yeah, I will need to make it longer. But what do you mean by a tensor?
You have two projection made operators. So you can tensor them and do it on a 6 or whatever, like 8 size. So send 0 to 0, 0, 0 plus plus plus.
Right. So you were suggesting to basically concatenate these two codes together and just putting them one next to each other. Like 0, 0, 0 plus plus plus. So 0 will go to 0, 0, 0 plus 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 and 1 to 1, 1, 1 minus minus minus. Do you accept?
No.
No, why not?
What if x is every occurring parts with plus and minus?
Yeah, so now I can correct zeros where I could correct them before. But now if an x error occurred there, I will not be able to correct it.
What if you change the order in one term? If you do 0, 0, 0 plus plus plus, the other one will be minus 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 1, 1, 1.
They are not orthogonal. They are not orthogonal states. So, okay, so I'm not claiming that the following solution is the only solution, but let me give you a solution. That's called the 9-qubit code of Shor. Okay, so Shor's 9-qubit code is basically his idea. It's a 9-qubit code, as the name suggests, and his idea is to take each one of the qubits in the encoded state and encode it by the other code. Okay, so let me write it down. So 0 is going to go to plus. Actually, I'm not sure what's the direction. Just a moment. 0, 0, 0 plus 1, 1, 1 over square root of 2. Yeah, it should be over square root of 2. Okay. This to the third, and 1 will go to 0, 0, 0 minus 1, 1, 1 over square root of 2 to the 3. So what I did here is I first encoded 0 by the Z code. So I first took 0 and I encoded to plus plus plus. So it's 0 plus 1, 0 plus 1, 0 plus 1. And then in each one of those qubits, I spread them to 0 went to 0, 0, 0, and 1 went to 1, 1, 1. And this is how I got this state. And here I started with a minus times minus times minus, and each minus got spread, repeated on 3 qubits. Okay, so now I'm claiming that this code is actually a quantum error correcting code, and it corrects both x and z. And we'll see that it in fact corrects any 1-qubit error. So let's see. Maybe I should actually write it. I don't know, it takes a long time, but I think it's better. But I'm shortening it. Okay, and then 0, 0, 0 minus 1, 1, 1 over square root of 2. And then 0, 0, 0 minus 1, 1, 1 over square root of 2. Good. So 9-qubit code. Now let's see why we can correct for every error. Of course, I'm not going to write the spaces. What we're going to really see, I hope to convince you that it's going to work nicely, but we're not going to prove it completely. So, almost. Okay, to suppose an X error occurred in one of those blocks, what do? Suppose an X error occurred here, so say this middle qubit flipped. How would we correct such an error? Kind of natural.
Formats again on the second.
Yeah, that's if we know, but first we need to measure. So what would we measure?
Space that we need to append all this to 3 qubits state, right?
Right, so I think what you're saying, if I understood correctly, is tensor with identity and everything else. And here, apply exactly the same measurement that we had before, right? It's exactly, this state should be exactly in the same state that we had before. Same thing for here and for here. So a single X error I can correct. What about a single Z error? Let's fix it back. What about a single Z error? So we know that a single Z error, say here in the left qubit of this second block, what does it do? It flips the sign, so we have minus here and plus here. So now how would you suggest to correct this?
Between different.
So I think you can see that basically you have exactly the same situation as before, except there is redundancy. So we will do exactly as before, except where the spaces that before were defined by plus, 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 minus, 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 now plus is spread over 3 qubits. So it's 0, 0, 0, plus 1, 1, 1. And it's the same thing, exactly. So same measurement. So we can perform these measurements and we can correct a Z error and the next error. And let's see that we can also correct a situation in which both X and Z occurred on the same qubit. So suppose now we had a Z error. Where did it go? It had a Z error, say, on this qubit. So now we are flipping it by an X error. Does it disturb us? No. We do exactly the same thing. We first correct for the X error. We find that there was an X error here. Nothing happened here. We flip it, and we're back to the previous situation. So we can correct X, Z, and X times Z, which let's call it Y. And of course we can correct for identity. Nothing happened on Q. Good. So now I'm claiming that this corrects for any error. Yeah.
Why don't we worry about things like X plus?
We do. I mean, X plus, so these are unitary, so X plus D is not unitary. But we're not restricting ourselves to unitary operators. We're restricting ourselves to unitary operators acting on this qubit plus the environment. So we should worry on everything that can happen to a single qubit, even if the environment or whoever creates the errors decides to take this qubit and perform a whole quantum computation on that plus other things. So you're right that this is not the only thing that we need to worry about.
I just mean like you keep all the examples are splitting a bit inside of a single K, whereas couldn't the general operator, the general unitary, make us split the K into, instead of just making it 0, 0, 0, 1, 0, 0, it could make it 1, 0, 0 plus 0, 0, 0.
No, that's a more general error. For that you have to touch more qubits.
I think XYZ also expanded the basis for SUT matrix. So if you can correct this, you correct all the.
Yeah. So basically, what's your name?
I'm John.
John. So John suggests exactly the right solution. These 4 matrices span all 2 by 2 matrices. Right? They're independent as matrices. So essentially this is the underlying idea of why any error, if you can correct an error of this type, any error of this type, you can correct any error whatsoever. If you want to be a little bit more sophisticated, you can think of a general error on a single qubit as a unitary operator on that qubit plus something else. And we haven't really said that. I think Thomas, I'm not sure if you said that, that every operator can be, every operator, including measurements, including whatever you want, can be represented as a unitary operator acting on a slightly larger system. We didn't say that. Let me give an example because this is important. Suppose I measure a qubit, so this is our remark, okay? Suppose I have a qubit A0 plus B1. And I'm measuring it. We know already what we get. We have 0 or 1, right? We collapse to either 0 or 1. With probability A squared, we collapse to 0. With probability B squared, we collapse to 1. Now, I want to mimic the effect on this qubit by a different thing, so that the reduced density matrix will have the same effect. Okay? I'm looking for a unitary acting on this qubit tensor with, say, 0, such that when I take the reduced density matrix to this qubit, it will have exactly the same effect. It will look the same. Okay, so I'm claiming, maybe you already have an idea of what that would be. I'm claiming that if I apply the C0 on this state and this state, so that brings me to A00 plus B11, and I now take the reduced density matrix to the first qubit. We've essentially done that, right? For EPR, when A and B are 1 over square root of 2, we did that. And we saw that we get a coin flip. Here, we will get a coin flip with probabilities A squared and B squared. So the effect on the qubit is the same. So this is a general thing that you should know. Any operator that you do, whatever you do, if you extend the Hilbert space by a few more qubits, you can make it unitary. Any operator that is allowed physically, including measurements, that is. Good. So now the most general error is a unitary acting on the qubit plus some environment. That's the most general error. So I have some operator U. Let me erase this. U acting on my qubit. I don't know how to write it exactly. Okay, I have an operator U acting on qubit 1 in the state and on the environment. And my state in the beginning was psi tensor the state of the environment. And my operator this is a 9 qubit state, and my operator U acted say on the, I don't know, the 4th qubit and on the environment. Okay, so let's say the environment is 2 qubits. So it's a 3 qubit operator which does something to this 4th qubit and the environment. Okay, the setting is clear? What I want to show is that essentially this U can be written as X tensor something on the environment plus Y tensor UY on the environment plus Z tensor UZ plus I tensor UI. Where these U's need not be unitaries, some operators. Okay? And this is a true bilinearity. If you don't really believe me, which you shouldn't, check it later. Okay? But it's pretty believable because these span the space of 2 by 2 matrices. So every unitary I can write as doing this. Tensor was doing something to the environment. if I can correct this, I can, that's it. I'm done. So, yeah.
I'm sorry, is this related to what Thomas was saying that we can add more wires to make it reversible? If you have something that is not reversible or invertible, then to make it unitary.
Yeah. Yeah. Doing something irreversible is like a non-unitary operator, and you can extend it to unitary by copying, essentially. Good, thanks. Okay, questions about this? This is our first quantum code, which can correct the general one-qubit error. And it also solved this problem of continuity, right?
I don't understand. So it will correct an X or a Y or a Z because your measurement falls into an eigenspace that identifies a specific error, right?
That's true.
If you have a linear combination, you will get some. What are you going to get?
What you're actually going to get is, allow me to cheat a little bit, you're actually going to get the projection on one of them. So you'll measure, and you'll find which one happened. So if this was the error, and it was a linear combination, when you perform this measurement, here assume that the error was one of these four possibilities, and then my measurement didn't do anything. It just told me the information. But here, the measurement will actually collapse the state to the subspace that corresponds to that error.
This can be radical, right? The error can be a small error, so it drives you out of the correct space in a certain direction, and you make a measurement to ask, was there an error all the way in? And that measurement might tell you there was no error. If it tells you there was no error, it just drove you back to where you were. Or if it tells you there is an error, it means it drove you all the way there, and then you see there's an error there, and then you just flip it and get back there. So the error can be any kind of continuous thing, but either you don't see it, which means you basically corrected it at the same time. You didn't see it, you made it.
It might help me to just see how the correction process works for just like a measurement there. Let's say like one bit was measured and how it's corrected, if we have time.
You're right that it will help, but I don't have time to go into this. But I'm happy to say it afterwards. Yeah, this is something that I want. I agree that it's very surprising, and indeed it was very surprising. It's not. I mean, the fact that you can correct a measurement, you can go to a qubit, you measure it. If you measure this qubit, you've collapsed the state to 0, 0, 0 without the 1, 1, 1, 1, and still you can correct it. Okay. And it looks like you've affected the 3 qubits, not just 1. Right? But as Thomas said, this measurement will with some probability, will just project you back to that state. That's with probability half. The measurement with respect to whether an error occurred or not. Essentially, just to say one more word about it, a measurement can be considered as a linear combination of applying I and Z. And so it will give you, with probability half, nothing happened, with probability half, a Z happened. Okay, I'll just do it. If you have a density matrix,
Joey,
yeah.
Maybe give yourself some space to use it so that you can write it large enough.
Actually, Thomas, I think I'll take that as also a reminder of the time. So maybe I know he didn't make it, but it was actually, I think I should. I owe you one. So
I wanted to see it.
you wanted to see it? Okay. Okay, but then we might wait 5 minutes for the pizza. So suppose we have a density matrix, rho, which is A, B, C, D of a single qubit.
You can also eat while you talk.
Yeah, that would be nice for me. Actually, I don't mind. So ABCD is the density matrix, and what happens to the density matrix if I apply a Z to it, to the qubit? You know? So if I have A0 plus B1, the density matrix is A squared, AB, I'm ignoring complex numbers, B squared. What happens if I apply a Z to this state? What happens to the density matrix? It gets a minus sign here, right? So if I take with probability half nothing, and with probability half a Z, what's the resulting density matrix? Just the diagonal, the off-diagonal terms disappear. And we've seen before that this is exactly what happens by a measurement. Okay, so great, this is our first quantum code. Okay, it's one code. We need some machinery to design better codes, and there is a lot of machinery for that. Okay, so first of all, I want from now on to restrict myself to just errors of the form IXYZ. So these are errors of the form of the Pauli errors. So products of matrices IXYZ on one qubit, and we'll be talking actually about errors that can happen to many qubits. So products like that are called Pauli errors. Okay? So I, X, Y, Z are called Pauli matrices, and products of them to tensor n with including phases I, minus I, and plus minus 1, this is the Pauli group. That's denoted by Pn. Okay? And we'll be talking about errors that affected, say, at most T qubits and did nothing to the rest. So say an error of this type. I, X, Y, Z, I. What's the weight of this error? I would say it's 3. Okay? And so I'm calling the weight of a Pauli error is just the number of places where it's not identity. Okay? So now, first of all, we can define a quantum code, an NK quantum code is a k-dimensional Hilbert space subspace of let's just write it, the space of n qubits. Okay, and we will say that it can correct any error on T qubits, on any T qubits, which for us, as we've seen, is just the same as any error of any Pauli error on T qubits. We'll say that if, so it can correct any Pauli error E, such that E is less than most T. If for any such error, if there exists, some unitary R, that's the recovery, which acts on the space of, on the qubits of the code plus maybe ancilla qubits, not maybe necessarily ancilla qubits, such that for all psi in the code, let's call the code C.
But the code is supposed to be an encoding of k qubits.
Mhm.
Why did it have dimension k?
It's dimension 2 to the k. It's sometimes confused in the literature. People call it dimension k. Let's call it 2 to the k. Thank you. If there exists R such that for all psi in the code, C, R psi tensor 0, so R acts on these ancilla bits initialized to 0, R acting on E, acting on psi, what do I expect? Psi, but, so it's going to be tensor with some state, and because it's unitary, it's necessarily this state has to depend on E, but it should not depend on psi. Okay, that's what we mean by a code that can correct T errors. Okay, so what are the conditions for such an error correction? So I'm not going to prove anything about these conditions, but I do want to give you some idea about those conditions and where they differ from the classical case. Because this is not only very interesting from the point of view of quantum error correction, but it's also interesting from the point of view of quantum entanglement and understanding global entanglement. So now is your time to ask the question. In a moment. So what are the conditions for error correction? So such a correction will be possible. Correction of a set of errors EA. Okay, let's just denote it. The index will be A. EA is possible if and only if for all psi I, so I'll write this in a moment, if and only if psi I E dagger A EB, these are two errors that can occur, psi j is equal to CAB delta ij if psi I over I is a basis, an autonomous basis for C. So let's stare at this for a moment. This is the okay, so I have a basis for the code, psi I, and I want to know when is it possible to correct the errors. So one side of this equality, so sort of one case of this equality seems very natural. Suppose I is different than j. Okay, let's take I and j different. So we're talking about two different states in the code. I already raised this feature, but it's very natural that we are asking that I cannot be confused between two words in the code. This is the jth word after applying an error. And if this is not, if the inner product is not 0, suppose it's 1, then if we apply on psi j EB, we got some state. And that state can be confused with applying EA on psi I. You see what I'm saying? Can I say it again? Let me say it in the classical version first. If I have a string, and I have another string which is close to it, distance d, and I know that that's exactly d over 2 errors occurred, then I don't know if I came from here or from here. Okay? This is the same situation that happens here. Suppose this inner product is 1. So, meaning that this state is equal to this state. So then, if I reached this state, I don't know if I need to go back to psi j or I need to correct to psi I. So this is very natural. The condition that when I is different than j, this will be 0, that's the delta ij, this is very natural. Yeah? Okay. What's not natural is the other condition. When I is equal to j, let's see what that means. So when I is equal to j, delta ij is 1. And what does it mean? It means that psi I, Ea, Eb, psi I is some constant CAB. The key point here is that CAB doesn't depend on I. Okay, what does this mean? Sorry? I didn't get the question. Project-
The other question was, I guess, said that it means that you can project, you can measure without collapse.
Doesn't CAB only depend on the error, not on the chosen basis of psi? So essentially, when you have the conjugate for EA or the dagger in EB, CAB is strictly dependent on the single error that occurs to the true code.
CAB does depend on the error.
Yes, that's my point. It only depends on the error.
Right. But what I'm asking is, why do we expect it not to depend on I?
Because we want to distinguish between errors. We want to understand which error occurred. And if it depends on I, we may have a coincide situation. And we can say we have the error on this state, this error on this state, or then another error on another state. So they shouldn't depend.
Okay, it's. I think what you mean is very close to what I want to say. Shachar, do you want to say?
Still not understand my sense of that. So let's say you didn't have this condition.
Sorry?
Let's say you didn't have this condition for I equal to j, right?
Right.
So for I orthogonal to j, then you can still say, let's take the space of C and A that you might put on it. So these spaces are all orthogonal to each other. So you can have a measurement that would measure to one of them.
Let's just do this. This is my code. Okay?
Okay.
And let's see the conditions for this code. What's the size so suppose I is different than j. So we're talking about this is 0, 0, 0, and this is 1, 1, 1. How many bits do we have to change in order to move from one to another? 3. Okay? So we should be able, so it will be 0 if this is just one error and this is one error. Okay? So this condition is the first condition is satisfied. It's actually the classical condition. What about the other condition? The other condition is not satisfied because let's see, if this is 0, 0, 0 and this is 1, 1, 1, well, if this is 0, 0, 0 and this is 0, 0, 0, and here I have something that acts differently for 0 or for 1, then so essentially this is a Pauli operator. So just for the sake of the argument, think of this because Pauli operators span everything. Think of this as a measurement. So if it's a measurement, it will distinguish between, say it's a projection on 0. It will distinguish between the zeros and the ones. So it's not satisfied. And this is the key. The key for understanding quantum error correcting codes is that not only do we need to build a subspace which is hard to move from one to another, like in a classical case, by small steps that don't touch too many qubits, but we also need to treat the environment as some kind of an eavesdropper. So we also need to I need my hands for that. We also need to think of the environment as some kind of an eavesdropper that tries to understand the information hidden in the quantum code by addressing it locally. If it could address the information that we're trying to hide, that's called the logical information. If it could address it locally, then it could essentially partially measure that information. And we already know that if it knows something about that information, by no cloning, it knows something, we cannot recover it fully. Because the information leaked to the environment, if we recover it, it was copied. So the environment must not have any access to the logical information that we want to recover. It's a kind of a secret sharing game, or secret hiding game, where we want to hide the information that we actually want to encode has to be encoded in its local sense. It cannot be encoded locally. Okay? Yeah.
Also, I don't know if this is true, but I think it may be. So if CAB also depended on I, it would challenge the decomposition of U as unitary because it would imply that there's a lack of orthogonality there. Because then, if CAB depended on I or J, like we said, then you'd have projections between some of those X and Z, and we know that X or Y, and we know that those are orthogonal, so that can never be precise.
I'm not sure. Is this a question or?
Right.
I
I don't know, but I wonder if that is the reason because if CAB depended on I, like I said, it would imply some kind of global dependence, and that would challenge whether X, Y, and Z are orthogonal, right? Because essentially, EA dagger and EB come from some U of that form that's written on the right. It's some error that happens.
We'll need to talk about it offline. I don't really understand it. Sorry. So, okay, so now I have to decide. What do I drop? And let me just say, the distance of the code is the first size in which this condition doesn't hold. I won't write it exactly, you can easily find it in the notes we put. But it's the first, EAs are of size t. So EA times EB is of size 2t. So the distance is the first time where this is not satisfied, it will be 2t plus 1, essentially. Okay. So what should we give up? Okay, we could try. I want to give you a taste of stabilizer codes. Stabilizer codes is basically the most, most commonly used framework to design quantum codes. It's not the only framework, but it's very, very useful. And one of the reasons it's very useful is because it can rely on classical intuition. Yeah.
So one more thing about this precise approach to error correction. It seems like basically you need to have 3 times as many qubits to do a computation. Why is it better to do this than have 3 quantum computers or maybe 4? Like it's harder to make.
Okay, good point. If you have n qubits in which you do the computation, then one of them will definitely die at some point. So with exponentially good probability. So you will need exponentially many repetitions. So you need to do something during the computation in order to correct all the time. You can't just repeat the computation again and again and again. Okay. So, so what are stabilizer codes? So we've defined the quantum code as, it was written here but it got lost, as some subspace spanned by the states that 0 goes to and the states that 1 goes to. Okay, the 9-qubit code, we had 2 states, so it's a 2-dimensional space. We can define this subspace in a different way, not by its basis vectors, but by what's called a stabilizer, meaning by a set of operators such that this subspace will be the only subspace that is a one eigen, that contains the one eigenvectors of these operators. Okay, so for each one of the operators, there will be eigenvectors of eigenvalue 1, and the subspace will be all vectors that are eigenvalue 1 of all operators. Okay, this will be the stabilizer code. So it's just a different way to define the code as a subspace, stabilizer codes. So we'll define it this way. First of all, we define the Pauli group already, and the stabilizer code is given by, say, I don't know, k stabilizers, all belonging to the Pauli group on n qubits. So they're all operators. Say, I don't know, XX, IXX. I don't want to give examples. Something like that. Okay? What are the eigenvalues of this operator? What are the possible eigenvalues of this operator? Just a set, don't compute it, but just where are they taken from? 1 and minus 1. And it's true for any Pauli operator, it's just always 1 or minus 1. It's also true for any Pauli operator that it's either commuting or anti-commuting. Okay? So we'll take k stabilizers which commute all together. And we'll require that our code will be the intersection of the one eigenspaces of all of them. So the code will be the intersection of the one eigenspace of Si, it's denoted by this, over all I.
So if you have k, then you get the dimension n state.
I'm sorry?
So if you take k of z, then you get the code of dimension n minus k.
Yes. If they're independent. Okay. So this will be our code. And the reason we took the stabilizers to commute is that now we can actually measure all of them simultaneously. The measurement doesn't disturb. And so we can actually decide whether the state is in the code, it's stabilized by everything, or not. So let's just see what happens if yes or if no. So let's suppose we have an error. Suppose we have an error on a state in the code. And I want to look at the commutation relations between that error and all the stabilizers. So suppose this error commutes with all stabilizers. Remember, it's either commuting or anti-commuting. Suppose it commutes with everybody. So let's see. I just want to see if what's this. What happens to this state? What's this new state? So I'm claiming this new state, if E commutes with all the stabilizers, is also a word in the code. So if E S equals SE for all S in the stabilizer group, that's a group actually. You can look at all the group generated by all these elements, and they still commute. And so for all stabilizers in S, then each psi is also in the code. Why is that? I just have to check that SE psi is equal to E psi. And why is that? Well, SE psi for some stabilizer, well, it commutes, so it's ES psi, and S psi is psi, so that's E psi. So if E commutes with everything, then it takes a word in the code to a word in the code. It doesn't necessarily have to be the same word. We call this a logical operator. It's an operator that does something in the code, so it does something logical. It takes encoded words to encoded words, and we cannot detect it. It doesn't do anything that it leaves the words in the code. And we are trying to avoid such small logical operators because we will not be able to detect them. Okay, what happens if there is a word, an error, E, that does not commute with S? Well, then that doesn't happen. And this is how we will detect. So in fact, the set of stabilizers, generators, such that SE is equal to minus ES. That is, if you're familiar with this notion, this is our syndrome. This is how we will be able to detect the error. So basically what we will need to measure is whether this error commutes with the stabilizer or not. So how do we measure that? Any idea? Suppose there was an error, I have the stabilizer, and I want to know if whatever happened to the state commutes with the stabilizer or not. What would I measure?
S plus I.
Not S plus I would just measure S.
Yeah.
S is an operator, it has plus or minus eigenvalues. If I measure psi with respect to this operator, and it's an eigenvalue with eigenvalue 1, I will get 1. And if E and S don't commute, they anti-commute, then S E psi is equal, because of the anti-commutation, to minus E S psi, which is equal to minus E psi. So E psi is a minus 1 eigenvector of S. So I can just measure the stabilizers and discover they commute. I can measure them all together. The measurements don't disturb. And if I got all ones, then the state is in the code. If I got some minuses, the state is not in the code. And I know which stabilizers were wrong, so I hope I can correct. So when will I be able to correct? When will I be able to correct? So suppose the smallest logical error, the one that commutes with all the stabilizers, is of size D. Okay, suppose the any logical error is of size larger than D. I'm claiming that I can correct any error of size less than D over 2. Then we can correct errors of size at most D over 2. Why? Because any two such errors will have a different syndrome. Do you see why? Because any two such errors will have a different syndrome. Why is that? Because the product, the difference in meaning a plus or a minus 1. So if I have two errors which are small, and they have syndromes, plus, minus, 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 plus for the first error, and minus, minus, plus, minus, minus for the second error. What happens if I apply them both? I first apply E1 and then I apply E2 on the state. What will be the syndrome of the product of these? It will be the product of the syndromes. And if the syndromes are the same, it will be 1, which means that E1 times E2 is a logical operator, because it's 1 everywhere. So they can't be too small, okay? So we need to somehow define stabilizer codes with large logical operators. And if you've heard about the Torah code, I will explain this tomorrow. That's perhaps the most beautiful code I've seen. It's really beautiful. It has topological properties, and its logical errors somehow have to somehow wrap around the torus in order to be errors that somehow deceive us so that we don't detect them. So I'll explain this tomorrow. Okay, before we end, I do want to take 5 minutes from the pizza to just say something about fault tolerance. I don't think I'll even write on the board. Maybe. Okay, so these are polymer correction codes, and there are lots. You can have a whole course on them. They're really very beautiful objects. How do you use them to perform computation in the presence of errors? What's the problem in doing that? So the idea would be you would want to perform a computation on states which are encoded using quantum error correction codes. And then when errors occur, you want to correct, right? So the problem is that while you're correcting the errors, more errors occur. Okay, so you're sort of fighting against something that keeps accumulating, and the problem is that you don't know who wins. So the first problem is that if you're trying, so for example, okay, we'll draw something, maybe I won't write. So, for example, suppose I had an encoded word encoding 0. Okay, let's call it psi 0. It's a code on 9-qubit. It's a 9-qubit code. And now I wanted to perform a gate on it. I don't know, a Hadamard. Okay? So I wanted to do something on the state so that the resulting state will be still encoded, so that it's protected from errors. So I want to perform something here, a set of gates, I don't know, blanc, such that the result is psi 0 plus psi 1 over square root of 2. Now, if this blah thing here just acts on everything, it's a general circuit, then if a gate here was problematic, just a single gate, then through the interactions between the different gates, this error could propagate to many places. Okay, if an error here interacted through a gate with a qubit which didn't have an error, that clean qubit would now become contaminated. And so the error can propagate. And when it gets to the end, I will get here some corrupted state, which I won't be able to correct. So the idea is to design the procedures, the fault-tolerant procedures, in a fault-tolerant way, so that errors don't propagate too much. Okay? And then you cannot really hope for a situation in which there are no errors at all. But you can keep the errors below a certain threshold, so that errors accumulate, you correct, accumulate, correct. And if the rate of the error is small enough, then you're fine. Now, I won't go more into it. Maybe we'll, I don't know, maybe in the open question I can say a few more words. But let's have pizza now. Unless we want some, I don't know if there's a question. Is there a question to end this before the pizza? Yeah, let's have just one question.
Why do you think about like local large errors instead of tiny spread out errors or something like that?
First of all, it's wishful thinking. These are the areas we know how to deal with. But physicists tell us that this is something that is reasonable. If you separate the qubits enough, then it makes sense that the errors will be local. Just like local Hamiltonians are local by
If you separate them, then you can interact, right?
exactly. So if you separate that, so it's a trade-off. First of all, you need to maintain it in isolation, the entire system, and indeed, in order to allow interactions, you have to allow interactions.
Also, the local Hamiltonians didn't assume that the indices are close by. They want the x1 and xn, right? So somehow.
Yeah. So let me just say, it's not that bad. It's actually much better. You can handle errors in gates, so you're allowed to interact between qubits that are far away, interact them in a gate, and assume that they have some error in that gate, acting on both of them and correlating them. As long as the scale of the errors decays in some nice polynomial but not linear way, then you're fine. Okay? So you can have errors in gates, you can have systematic errors. You can have many things as long as there is some locality.
Can you get for this code the same parameters you get for the classical codes?
You can get good codes, meaning you can have codes with rates which are with positive rates and positive distance. I didn't talk about approximate codes, so I won't mention it. But if you want these type of codes, then no, then you can't actually correct half the errors. You will only be able to correct a quarter of the errors. Okay, so now let's have pizza.